the topic Newton's law of cooling or warming for our MAT300 group project.
For the introduction, Newton's law of cooling or warming states that the rate of change of the temperature of body is proportional to the difference between the body temperature and the temperature of the surrounding medium. So, in this topic, formula that we use is Newton's law, which is dt capital Zeta over dt small letters equal to k in bracket t minus ts close bracket. It is when k is a constant, t in bracket t small letter is temperature of the object for t more than 0, and ts is the temperature of the medium around the object.
Okay, now let's look at the problem statement. So the question is a small metal bar whose initial temperature was 20 degrees Celsius is dropped into a large container of boiling water. How long will it take the bar to reach 90 degrees Celsius if it is known that its temperature increased 2 degrees Celsius in 1 second? How long will it take the bar to reach 98 degrees Celsius?
Let's start by solve this solution. First, the initial temperatures when 20 degrees Celsius. As we know, the initial is start by 0, then T0 equal to 20. We use the formula Newton laws when the rate of change of the temperature of the bar is proportional to the difference between the bar temperatures T and the surrounding temperatures 100 degrees Celsius, which is the boiler water temperatures. This gives us the differential equation dt per dt equal to k multiply bracket t minus 100 close bracket. To solve the equation, we integrate both sides. The left hand side is the temperatures of the bar and the right hand side is the simple equation in both times. Integrate dt per dt equal to integrate k dt. The integrate of dt per dt give us the temperature change, and the integral of k dt give us k multiply t. So after integrate, we get ln t minus 100 equal to k multiply t plus c. Where c is a constant of the integration. Then we can solve the t time by exponenting both sides. T minus 100 equal to exponent kt plus c. We can rewrite the constant of integration as a new constant. Let's say c exponent c, where c is the initial value when t equal to 0. This gives us t time equal to 100 plus c exponent kt. Next, we apply the initial condition. As we know, at t equals 0, the initial temperature of the bar T0 is 20 degrees Celsius. For we substitute small t equal to 0 and t equal to 20 into the equation to find the constant c. When a 20 equal to 100 plus c multiply exponent k multiply 0. Simplifying this give 20 equal to 100 plus c. Next, we solve for c. We get c equal to 20 minus 100 and we get minus 18. So the final equation for temperatures, we can substitute c equal to minus 18 back into the equation for t times. So we can get the final which t time equal to 100 minus 8t multiply exponent kt.
Now let us determine the value of k, which is the rate constant in our equation. From the problem, we know that at time t equal to 1 second, the temperature of the metal bar is 22 degrees Celsius. Substitute this information into the equation. The temperature at time t equals 100 minus 80 multiplied by the exponential of k times t. We can write 22 equals 100 minus 80 multiplied by the exponential of k times 1. Next, we simplify this equation. Subtract 100 from 22, which gives negative 78. This makes negative 78 equals negative 80 multiplied by the exponential of t. Now, divide both sides by negative 80, resulting in negative 78 divided by negative 80 equals the exponential of k. To isolate k, we take the natural logarithm of negative 78 divided by negative 80, which simplifies to 39 divided by 40. Thus, k equals the natural logarithm of 39 divided by 40. When we evaluate this, we find that k is approximately negative 0.0253. Therefore, the rate constant k for this problem is negative 0.0253. So, the substitute value of k in the equation and get the temperature at time equals 100 minus 80 multiplied by the exponential of negative 0.0253 times t.
Now let's solve for the time it's taken for the metal bar to reach a temperature of 90 degrees Celsius. First, we need to substitute 90 degrees Celsius in Newton's law of heating that we get. Then we can simplify the equation to 1 over 8 equal exponent to the power of negative 0.0253. So now we need to put ln for both sides, and we need to simplify it again, and we get t equal to ln 1 over 8 per negative 0.0253. So the final answer is 82.19 seconds.
Next, for the temperature, we get 98 in the question. So 98 equals to 100 minus 80 E minus 0.0253T. Next, we will get 1 over 40 equals to E minus 0.0253T. After that, we change the place to get T equals to ln 1 over 40 over negative 0.0253. The answer will be 145.81 S.
The conclusion of this solution, we can calculate how long it would take for a small metal bar that was initially at 20 degrees Celsius to warm up when thrown into a boiling water that was at 100 degrees Celsius using Newton's laws of cooling or warming. Given that the temperature increased by 2 degrees Celsius in the first second, we apply the law principle that the rate of temperature change is proportional to the difference between the object temperatures and its surrounding. Through conclusion, we determine the time required for the bar to reach 90 degrees Celsius and 98 degrees Celsius. This problem demonstrates the low utility in predicting temperature change in heating processes and highlight how the rate of change slow as the bar approach the water temperatures. This application emphasizes the practical importance of understanding thermodynamics in real-world scenario.